Welcome to another episode in this series where I'm solving textbook problems. This is the James Stewart Calculus Early Transcendental textbook, the 7th edition, and we're working a bunch of integrals from section 7.5. Okay, we left off on 44 from the last episode, so let's continue. We have this integral square root of 1 plus e to the x dx. Okay, so how do we go about this? I don't see an obvious substitution. Like, if I set u to be something, du I see a signature of inside the integral. I don't quite see that. Is it by parts? It might be doable by parts, because it is technically a product of two things. It's square root of 1 plus e to x times 1. So maybe we can try that. It's not a trig integral, clearly. Not quite a trig sub, because it's not something squared plus something squared. Well, technically, you can force this to be something squared, but I think it's not like x squared or x to the 4, something like that, some power function like that. This is an exponential function. So probably not trig sub, and clearly it's not a rational function. So let me just try substitution, because that's probably one of the easier methods to see if we can get anywhere before I try it even by parts. So maybe let's let u be the whole square root term. Okay. Why do I want to do that? Well, as I said, if I let u just be just 1 plus e to x, du would be e to x dx, which I don't quite see a signature of. So let's find du, but remember we can do u squared first, is 1 plus e to the x. Okay. And then we differentiate 2u. Du would be e to the x dx. So there's still a e to x dx here, which I could have expected. I just wanted to show that I tried something, it didn't quite work. Okay, so, because once again, if I try to substitute dx in, I'll have 2u du over e to the x. E to x is u squared minus 1. Let me just try substituting in to show you. So we would get u times 2u du over e to the x. E to the x we can get as 2u, so the top becomes 2u squared du over e to x would be u squared minus 1. Oh, actually, we can simplify this. We could solve this integral. So this substitution looks like it could work. I actually did it a different way in a previous video, where I let u be just 1 plus e to the x, actually. Okay. I think my previous method was more roundabout. So let me just do it like this, actually. So see, sometimes even as I'm doing them again live, I'm not trying to look at my previous answer, but I was thinking in my head that this substitution might not work because it's e to x dx, but actually I can sub e to x as u squared minus 1, and then it becomes this guy. And actually this is the same thing I got in my previous time, but I went about a more roundabout way. So this is more direct, actually, it looks like. Okay, so how do we solve this guy? So let me say is equal to, let me say this is I, to make things clear. So this was my substitution. I is equal to this. Okay, so we can divide through by u squared minus 1. We can do long division, or remember, let's pull the 2 out first. So let me write it like this first. Let me go slowly. Okay, we can do a hack. Instead of doing long division, you can do this hack. U squared minus 1 plus 1 over u squared minus 1 du. Okay, so why would I want to do that? It'll be 2 integral of u squared minus 1 over u squared minus 1 plus 1 over u squared minus 1 du. Okay, and this simplifies to 2 integral of 1 plus 1 over u squared minus 1 du. Okay, this we can solve with partial fraction decomposition. This is just a simple integral. So let me rewrite it as 2 integral du plus 2 integral 1 over u squared minus 1 du. Okay? So as I said, I think I already said, I already forgot, this we can solve by partial fraction decomposition. So it'll be, we do on the side over here, we can say it's a over u plus 1 plus b over u minus 1 is equal to 1 over u plus 1, u minus 1. I factored this guy already as this. Okay, I believe I solved this exact partial fraction decomposition in a previous video, but let me do it again. Let's multiply both sides by this denominator, a u minus 1 plus b u plus 1 is equal to 1. We plug in u is 1. This would go away. 2b is 1. b is half. Plug in u is minus 1. This would go away. Then we get minus 2a is 1, so a is minus half. Okay, so we can directly, let me shift it back. Let me actually put a dotted box around this to show that my work. Okay, this is the partial fraction decomposition. Now back over here, this is just 2u, that's this guy, okay, plus 2 integral of a is negative half times 1 over u plus 1, and then plus half times 1 over u minus 1 du. Okay, and then I can actually distribute this 2 to both terms to make my life easier. So integral minus 1 over u plus 1 plus 1 over u minus 1 du. And now we are very close. It'll be 2u minus log absolute value u plus 1 plus log absolute value u minus 1 plus c. And then we're almost done. We just have to back substitute. What was a u? A u was square root of 1 plus e to the x. So 2 square root 1 plus e to the x minus log of, let's just square root of 1 plus e to the x plus 1 plus log square root 1 plus e to the x minus 1 plus c. This is what I get. Okay, so here the idea was I want to make a substitution to try to see if it became something more recognizable, which it was. Okay, again, you might be able to do this integration by parts, but it seems tedious, so I kind of did not want to do that. Okay, so as I said over here, what did I do over here? So I actually don't know why I crossed this out. I made this substitution, and then it became like this. And then I made another substitution in order to get back exactly what I got over here. So this is a more direct method to substitute. Okay, let's move on. Integral x to the fifth e to the minus x cubed dx. Okay, so here, how do we go about this? I see a product of two things. Like if it was just x to the fifth e to the x dx, then that's integration by parts. So maybe we have to use integration by parts somehow, but then I don't want to integrate e to the minus x cubed. That's going to be a headache. So let me maybe try to substitute that out. Let's say, let me call the variable p, because I know this one, you have to use integration by parts. So let me say its p is minus x cubed. So dp would be minus 3x squared dx. Okay, so let's substitute. Let's see what happens. Let's leave x to the fifth alone. E to the minus x cubed, that's e to the p. Okay, and then dx is dp over minus 3x squared. Put some parentheses to make it look a little nicer. Okay, so let's pull out the minus 1/3 as a constant. Okay, so we have e to the p dp times x to the fifth is still on top, and then x squared is on the bottom. Okay, so this is minus 1/3 integral we can simplify. So it'll be x cubed e to the p dp. Okay? So notice x cubed is minus p. So we can write it as 1/3 minus 1/3 integral of, let me write it as minus p e to the p dp. And then let's move this minus sign out. So 1/3 integral p e to the p dp. This is a classic integration by parts now. So the idea once again was, I know that if it's x to the fifth e to the x, or minus x even, dx, it'll be integration by parts. So maybe let's try substituting p as minus x cubed to see if we still get that kind of classic integration by parts form, which I did. Okay, so let me do the tabular method for integration by parts. So I want p to be my u. We're going to differentiate it until we get to 0. Okay, and then e to the p is left. We integrate it just as many times. Okay, so our integral is equal to, remember, plus minus, plus. We start from plus, let me alternate, and then we go diagonally. So it'll be p e to the p minus e to the p plus c. Okay, so what is p? Minus x cubed e to the minus x cubed minus e to the minus x cubed plus c. And that's my answer. And I forgot this 1/3, my bad. So, like this, 1/3 times this whole thing. Okay, so let me continue. 46 looks like we're on, right? So we have this integral x minus 1 e to the x over x squared dx. Okay, so here, for some reason, I really was able to tell this looks very similar to quotient rule. Okay, because if I distribute this out, let me do it on the side over here. So it'll be x e to the x minus e to the x over x squared. I just distributed the e to x to both terms on top. Okay? For some reason, to me, I was able to recognize this looks just like the quotient rule when we differentiate, because there's a bottom squared, if you remember, from the quotient rule. And then, so if x is the bottom, what would the top be? It looks like it's e. Okay, so let's double check. Bottom, d top derivative of e to x is e to x, minus top, d bottom derivative of x is just 1 over bottom squared. So I already found my answer. Okay, so let's say you weren't able to, so this is the answer, by the way, e to x over x, and then don't forget your plus c. Okay, so that would be the answer. Now let's say you weren't able to see that. I, for some reason, was able to tell right away. I actually don't know why. Maybe because I've been teaching quotient rule recently. So how would we go about this? Or even if this work isn't allowed, you're not allowed to show this type of work, then we have to use one of your techniques. What do you do? There's a product of things, so maybe let's use integration by parts, because remember, integration by parts is derived from the product rule. You can use the quotient rule, or this technically you can do the product rule, because it is the derivative of two products. It'll be derivative of e to the x and 1 over x. Okay, so maybe let's use integration by parts. Now, how to choose a u and how to choose a dv is the question now. Okay, if we didn't know this, okay, I would just choose, probably, because there's 3 things, I would choose 1 over x squared as my dv. I know how to find the integral of that. And then x minus 1 e to the x as my u. Okay, I'll probably want something differentiating, to me at least, is easier than integrating. So when it's, so I'll probably choose it like this. Okay, so du would be, here we need product rule. First d second plus second d first, or you can distribute it out. Doesn't matter. We still need product rule even if you distribute the e to x to both terms. But let me just do product rule directly. First d second plus second d first. Okay. V would be minus 1 over x. Got my dx up here. Okay. So maybe let's try expanding this du out a little bit. So it'll be x e to the x minus e to the x plus e to the x dx. We see that those can cancel. X e to the x dx. Okay, so let's do integration by parts. So if we call this guy I is equal to uv, so x minus 1 e to the x times minus 1 over x minus integral of v to u. So it'll become plus, because of this minus sign here, x e to x over x dx. And this is the first term. Let's write it the same. Okay, plus integral e to the x dx. And this is very easy. It just becomes plus e to the x plus c. Okay, let's factor out e to the x from both these terms. So what do we get? E to the x times x minus 1 times minus 1 over x plus 1 plus c. Okay, we continue to simplify because I wanted to make sure that I got this exactly. So let me take the steps. Technically from here, you should be okay, but let me show you that it does get back to that. Okay, let me multiply through, let me distribute the minus 1 over x to both these terms. So it'll be minus 1 over x. Sorry, this would be just minus 1, and this is plus 1 over x, plus 1 plus c. Okay, so now we can rewrite this now as e to the x times, let's combine these two fractions. I can make this as a fraction minus x over x. So it'll be 1 minus x over x plus 1 plus c. We're almost there. I'm just doing tedious work to show you that it does come out nicely to that. Now let's make this as a fraction. So it'll be 1 minus x plus x over x plus c, which is e to x times 1 over x plus c. And that's exactly what I was saying in the beginning. Okay? That's how I would solve this one. So once again, if you're able to recognize that this looks like quotient rule, then it made your life very easy. And now to show some work, and just in case you need to show a technique, we know that product rule and integration by parts are closely related. Well, integration by parts is derived from product rule, so that's what I did to show my work to get back this. Okay, and I'll call a part here that this problem went a little longer than normal, but that's okay. Please like this video if you found it helpful as always, and please subscribe also if you haven't already. And finally, please also look out for the next video. So hopefully I'll see you there. Bye.